So we also based on these encoding methods, we talk about the compression rate. We find that if we use 16 bits, for each character to encode such any document, you need too much file spaces. A lot of binary strings need to store them. So in the computer, we said we have not infinite space, right? We use finite memory space to do the storage or processing. So anyway, if we use all these 16 bits to character any number or any thing in this document, we cost too much space. So we need to transmit them in a very efficient way. So we talk about this concept of compression, which is a very important concept in the computers or computing systems. So we talk about three compression techniques. The first one is we call it keyword. Second one we call it run length. And third one we call it Huffman encoding. And all these three encoding algorithms, they are suitable for different situations. So let's check them in detail. So firstly, we talk about this keyword encoding. So we use keyword encoding, and it based a very simple concept is that in each text, we may occur several words or sentences. Basically, we consider the words, okay, each word. So the concept is that for each text, there may occur a lot of words. They frequently occurred. So we do not need to encode each word separately or respectively. We can reuse such frequently occurred words. Okay, so we replace them. We can replace them with a single character. For example, we in the English character in the English paragraphs, we may see this like as or the or and something like that very frequently used. So we just use a symbol to replace this word. So for example, this word need 2 characters, but with this, after this replacement, we only need 1 character. Similar like this. Firstly, originally it needs 5 characters, and we just use this symbol as an equivalent way to replace it, which only needs 1 symbol. Okay. And then when we do the encoding or decoding, we just check such kind of table we defined by ourselves for this keyword encoding. Okay, so the concept is frequently occurred keywords. Okay, so next. We show an example here. We use this keyword encoding. We give in a paragraph, okay, and then we define a keyword table like this. Then after the encoding, we can obtain this one as the encoded paragraph. So we can calculate the originally how much characters we use, and then this one times 16. This one times 16 because each character use 16 bits to represent. So this is how much bits we need to use to encode this paragraph. And then after the encoding, the character numbers are decreased. So this one also times 16, supposed to be how many bits it needs to represent the paragraph. So we can find that we saved 60 characters. So we use this one to divide it by this one. So we get this compression ratio is 90%. Okay, so this is how we calculate this compression ratio. Okay. Then the next one we talk about is this run length. The run length is differently used in the situation considered as the keyword in our daily used paragraph or in an article, something like that. It is more frequently like in the DNA sequence, something like that. Okay, so we replace a repeated sequence. So we use something like this. If we have a sequence like n, in a set of string where same character repeated, Then so such kind of situation, because it repeatedly, so we can use such kind of representation. We use a star to flag the character. It says hello, from this star, from this character, the following would be repeated character. So it's like a sign, okay, like a flag. And then the repeated character would be n, so we mark here this one and the repeated character. And we use a number to represent how many times it occurred. So how that is the number of the times it repeated. Okay, so supposed to be 8 here, so we can use this string with only 3 characters to replace this string. Exactly, okay, so they are equivalent, but we only use 3 strings to represent these original 8 strings. So here are 2 examples like here, okay. So for example here, so it's supposed to be star B, and we count how many B's occurred here. It's supposed to be 8. And here we can say this is also repeated string, but we do not character it or encode it use this run length encoding, right? That's because you can think it's only repeated 3 times. If we use such kind of encoding, run length encoding method, it's supposed to be star and J and 3. But it is also 3 characters. The same with the originally, so there's no necessary to encode such kind of strings, okay? And then for those smaller or equal or smaller than 2 repeated, like 1, 2, 3, the number of the how they repeated, we just keep them originally. And then this one we encode it like star, Q, and 6. And this one was supposed to be star, plus, and 5, okay? This is similar. So if we have an encoding test, we can directly write this original test, right? So this represents x repeated 4 times, so we can write it like this. This is p repeated 4 times. We can also write it like this. This one is just 1L. We keep it originally. And this one is k repeated 7 times, so we can write it like this. Okay. So we can find this type of repetition doesn't occur in English tests frequently, right? So in fact, it is frequently occurred like in DNA sequence or something like that. We need to find some specific situation to use that kind of encoding methods. So the third one would be an Huffman encoding, what we are going to talk about. Firstly, this encoding algorithm occurred due to an observation in that why should the character, for example, X and the character Z, they take up the same number of bits as E or a space. That is, for example, this character is 16 bits, and this character is also 16 bits. But it is obviously these characters may occur much more times than these characters. So the basic observation and the concept is supposed to be for each character that occurred in different frequencies. So we may use different lengths to encode such kind of characters. There's no necessary for all characters they use 16 bits to do the representation. So here we propose a concept is that we use a variable length bit strings to represent each character. So more frequently used letters, they're supposed to have shorter strings to represent them. So this is the basic concept of this, but we need to define how we do this, right? So let's check how we define. So it's something like this. We can define its Huffman code. For example, the frequently used AE, the most frequently used the character, and the less frequently used character, but also a little bit frequently, and exactly not frequently used. So we use 2 bits or 3 bits or 4 bits to represent them, and we define exactly what's the string to represent A and what's the string to represent E, and they cannot be repeat or the same, something like that. So when we do this Huffman encoding definition, we can check the table and write down what this supposed to be. Right, B is here like 1010, so we can write here, and A is supposed to be 00, and we can find here. And L is supposed to be 100 and 2 100 repeated. And then also B is 1010, where O is 110, where A is 001. Okay. 00, I'm sorry, 00, not 001, 00. Okay. And R is supposed to be 111. And D is supposed to be 1011. Okay. You can write its original string. So you can consider what's the compression ratio. If we use 4 for each character, it's supposed to be 56 56 bits to represent. But after we compress them, there are only 28 strings to do the representation. So we can get its compression ratio. Okay, so you can use this table to try to encode the road bed as an example after class. Okay, I will send these slides in our WeChat group, and you can do this after class. Do this exercise to try to figure this out by yourself more clearly. Okay, so that is how the Huffman coding work, and we can do the code and decode. And one thing is that when we do the decode, we look for match from the left to right. We do a lot of calculation from the right to left in the binary arithmetic. But in this Huffman coding, we also we always from the left to the right and bit by bit. Okay, bit by bit, and we record the letter when a match is found. Begin where you left off and going left to right. Okay, so this is how we decode them. So this is an example about how we decode them. We check this string and we firstly find 1, there's no, so we check 10, and there's still no, so we check like 101. And we find it's still no, so we check 1011, and we find here 1011, so it's supposed to be D. And here it is 1, there's no, 11 also no, 111 it is here, so it is an R. And then we can find the 00 is here for A. And 10 there's no, so 101 is also no, so 1010 is supposed to be B. Okay, so we can decode them. So you may check if we have 1011 here, so it would be no 1 or 10 or 101, such kind of definition in this table. Otherwise, it'd be confused or it would be a totally mistake. So this is how we do the Huffman coding.